Welcome to this explainer. Today, we're diving straight into a massive roadblock in space exploration, and we're looking at the wild, sci-fi turned reality tech that might actually get us to the stars, a spacecraft's propellantless propulsion potential. For decades now, chemically powered rockets have been the absolute workhorses of the space industry. I mean, they're what put humans on the moon and rovers on Mars. But if we want to venture further out, if we really want to become a true interstellar species, we're facing a massive fundamental physics problem. We are quite literally weighed down by the exact same thing that propels us. So, let's kick things off with a pretty mind-bending thought experiment. Take a look at this number, 10 to the 53rd power kilograms. Just wrap your head around that for a second, because that represents the estimated mass of the entire observable universe. Every star, every planet, every single galaxy we can possibly see. Now, you might be wondering, why on earth were we looking at the mass of the universe when we're talking about rocket engines? Well, it actually perfectly demonstrates the severe, fundamental limitations of the chemical combustion engines we rely on today. Here's the deal. Imagine if we could take that entire universe, every single ounce of matter at 10 to the 53 kilograms, and magically convert it all into chemical rocket fuel. And let's say we burn all of it just to push a payload the size of one single microscopic proton. You'd think it would go insanely fast, right? Well, according to the Tsiolkovsky rocket equation, which governs all conventional spaceflight, burning that astronomically impossible amount of fuel would still only accelerate our tiny proton to about 735 kilometers per second. That's a mere 0.002% the speed of light. It brutally illustrates the ultimate roadblock of space travel. Carrying fuel requires more fuel to carry that fuel, trapping us in this highly inefficient cycle. So that brings us to our first major shift, leaving fuel behind. Because chemical rockets convert only a tiny fraction of rest mass energy into actual kinetic energy, they simply can't reach interstellar speeds. To truly explore the cosmos, we need a radical pivot to propellantless propulsion, where we ditch the heavy tanks and surf the natural forces of the universe instead. Think about it like setting sail on the ocean. Instead of packing millions of gallons of gas to run an engine, you just catch the wind. That's exactly the paradigm shift we're looking at for spacecraft. By eliminating the need to carry propellant, we completely rewrite the rules on a spacecraft's mass, its mission duration, and its ultimate velocity. So the most obvious question is, if we aren't burning chemical propellants, what forces are out there waiting to be harnessed? Well, it turns out space is far from empty. Our solar system and even the interstellar void are completely filled with natural energy sources. We're talking immense gravitational fields, the continuous bombardment of electromagnetic radiation from the sun, supersonic plasma outflows, and even the bizarre bubbling energy of the quantum vacuum itself. Let's explore that first natural energy source, escaping with gravity assists. This is our first fully proven toolkit, and it basically involves stealing momentum directly from the planets themselves. And the best part? This doesn't require any advanced sci-fi technology. It just takes some brilliant orbital mechanics. By flying close to a planet, a spacecraft gets pulled right into its sphere of influence. Through the conservation of momentum, the planet physically transfers a tiny part of its orbital momentum to the craft. The spacecraft then departs with a much higher speed and an altered trajectory, flinging it deeper into space, while slowing the planet down by a completely unnoticeable fraction. And guys, this isn't just theory. Missions like Voyager and Cassini have already utilized this exact momentum exchange technique to traverse our solar system with barely any propellant. Voyager 1 launched way back in 1977, and it actually gained the energy it needed to escape the sun's gravity entirely just by performing these slingshot maneuvers around Jupiter and Saturn. More recently, the solar orbiter used Venus and Earth to dramatically alter its trajectory. So it's a proven, highly effective way to navigate, really only limited by the specific alignments of the planets at any given time. Next up, we're moving from gravity to riding the light. Here we are shifting from the gravity of planets to harnessing the electromagnetic radiation of the sun itself using solar sails. Now, photons don't have mass, but they absolutely carry momentum. When sunlight hits a perfectly reflective surface, it imparts a tiny push. Just how tiny? Well, in Earth's orbit, 1 square meter of a solar sail only produces about 9 micronewtons of force. To put that into perspective, that is roughly the equivalent to the weight of a small ant resting on your palm. I know, it sounds completely useless for moving a multi-ton spacecraft, doesn't it? But there's a pretty massive catch. What's really fascinating here is how that tiny, ant-sized force compounds over time. Because you aren't burning fuel, the engine never, ever turns off. That continuous push happens every second, every hour, every year. Over a long period, that continuous acceleration builds up to tremendous speeds. This turns solar sailing from a cool theoretical concept into a reality that's actually been proven by missions like Japan's Icaros in 2010 and the Planetary Society's LightSail 2. It absolutely proves that flight by light is a highly viable path for long-duration missions. But sunlight isn't the only thing the sun throws at us, which brings us to surfing the solar wind. The sun is constantly exhaling this crazy supersonic stream of charged plasma, mostly electrons and protons, traveling at unbelievable speeds of up to 800 kilometers per second. So let's compare the different architectures we could use to catch it. While solar sails ride light using giant physical sheets of reflective material, magnetic and electric sails act more like massive invisible nets. A magnetic sail generates a huge artificial magnetic field to deflect the solar wind. This gives you higher acceleration for sure, but it requires an immense amount of onboard power. Electric sails, on the other hand, take a very different, incredibly clever approach to deflecting those fast-moving protons. The electric sail, or e-sail, which was first proposed back in 2004, is particularly fascinating because it just uses thin, highly charged wires to repel the incoming solar protons. Imagine a spinning spacecraft extending dozens of lightweight conductive tethers outward. By keeping these tethers charged to a high positive potential, around 10 to 20 kilovolts, they create an electric field that repels the positively charged protons in the solar wind. That deflection actually pushes back on the tethers, producing a steady, continuous thrust that scales beautifully across the solar system, entirely with the mass of a giant physical sail. Okay, now let's take things to the absolute frontier, harnessing the quantum vacuum. We're going to blow our minds a little bit with some speculative quantum physics here. We've talked about gravity, photons, and plasma. But what if we could generate thrust from literally nowhere? Classical physics tells us that deep space is a pure, empty vacuum, but quantum field theory reveals a much stranger reality. The vacuum is actually characterized by microscopic, fluctuating fields of energy. It's basically boiling, with virtual photons just popping in and out of existence. It's not empty at all. It is a bubbling cauldron of potential energy. And scientists have been actively researching if these quantum fluctuations can be harnessed for space exploration. This brings us to the dynamic Casimir effect. It's this mind-bending concept where vibrating mirrors could literally shake real photons right out of the empty vacuum. If you take closely spaced plates in a vacuum and change their boundary conditions rapidly enough, like vibrating them at immense, unimaginable speeds, you can actually convert those fleeting virtual quantum fluctuations into real, measurable photons. And this brings us to the ultimate, far future goal of propellantless propulsion. If we could somehow perfectly control this asymmetric photon emission, literally shaking photons out of the vacuum and directing them out the back of a spacecraft, we could generate continuous thrust from the empty void of space itself. Now, just to be totally clear, right now this only works at a practically immeasurable nanoscale in highly controlled lab settings. The thrust produced is entirely too small for a macroscopic spacecraft, but the physics are completely real, and the implications for the future are absolutely staggering. So it leaves us with this incredible, provocative thought to take away. The rocket equations that successfully got us to the moon are fundamentally incapable of taking us to the stars. To truly become an interstellar species, our greatest engines might not burn any fuel at all. Instead, we'll have to gracefully sail the natural currents of the universe, riding the light of the sun, surfing the plasma winds, and perhaps one day extracting our momentum from the very fabric of the quantum vacuum itself. The fuel of the future, it seems, is no fuel at all.